It's time to look at overfitting the data. This is a major topic in machine learning. It's going to come up later today and throughout this summer program. I want to be sure that you understand it, so let's take a look at overfitting in some detail right now. Okay, let's start with the selection of random points. We're in 2 dimensions here. So the standard x-axis and a y-axis. And we want to take a look at polynomials. In particular, the question is, what degree of polynomial will fit the data best? Now, we are considering this as a machine learning problem. So it's not just about trying to fit those points perfectly. It's also the question of how well will the polynomial regression line fit new data that's coming in. Okay, that's what we mean by best fit. All right, so let's start with the first degree polynomial, the classic linear regression line. In this case, this is considered to have high bias. The idea behind bias is that the regression line is biased based upon assumptions that have been made that may not really fit the data at hand. Okay, this is the line of least squares, and you can see it doesn't really pick up on the pattern in the data. Okay, so this is what we call underfitting the data. And the regression line fails to pick up on nuances of the data. Okay, regression lines sometimes may work great, but in this case, yeah, it's going up a little bit, but you're not getting a whole lot out of that information. Now let's take a look at an 8th degree polynomial. So in this case, it fits the data points perfectly. This is considered to have high variance. The idea behind high variance is that the polynomial curve is going to vary considerably depending on which data points are chosen. Now, this is said to be overfitting the data. So let's take a look at that in some detail. The polynomial generalizes poorly to new data. Now, let's consider some different points on the curve. When x equals 1.5, y is going to be 11. That's the highest point by far. Does not really seem to be a good representation of the pattern that the data has. Well, when x is 8.5, you're getting y equals -3. So that's an even worse prediction. But then when x equals 10, you're looking at about 250. So these 3 data points are poorly chosen from this regression line. Curve and line are used synonymously often in, like you could say, machine learning world. So this is, again, the classic example of overfitting the data. No matter how many data points there are in 2 dimensions, you can always find a polynomial that's going to fit it perfectly. How many data points is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. 8th degree polynomial fits it perfectly. 1700, just get a 1701st degree polynomial to fit it perfectly. Okay, let's take a look at some other images here. So you tell me, what do you think fits the data better? The green line or the blue curve? Note here that it's fitting the data to the green dots, and the test dots would be like the red ones. And you can see the blue curve actually does a good job on a couple of the red points, but the second and third one actually are much closer to the green line. And it just seems evident that there is a linear pattern here, that the green line is a better fit for this data. This also is the problem of the ends, right? Close to 0. You look ahead of 45. Okay, here's another fun one. So you're trying to split the data and find a curve that's going to split the data into the red and the blue. And so which one would you take? The black curve or the green curve? So the green curve appears to split it actually perfectly. But again, this is what you call overfitting, right? It's like too precise. It's not going to generalize well to new data points. Like, for all you know, a couple of those red points could be mislabeled, okay? I think the black line is definitely better here. Even though it misses some of the points, it picks up in the generalities better. It's likely going to test better in data it has never seen before. So again, the green curve here is overfitting the data. Finally, let's take a look at an image here. This is actually a graph of the errors, okay? This is not saying, hey, which line fits better. It's saying, hey, this red curve is the error over time, over a different number of epochs, which are the number of, you think of it like the number of iterations, the number of rounds in machine learning. And the green shows you the test error. And then what happens, you notice, after about 50 epochs, the training error, that you're fitting the data on gets a little bit better, like the error goes a little bit down, but the testing error goes up, so it gets worse. That's when overfitting occurs. So what's happening is the machine learning model is trying so hard to pick up on those nuances of the data that it's going out of its way to circle specific training points at the cost of missing more testing points. So we can look at some point how to create a graph like that so that you can try to find the ideal number of epochs for building a model. So what are the solutions to overfitting? Well, we can adjust hyperparameters to generalize overfitting. You want to generalize better to new data, I think is the way to actually say that. And you want to include regularization techniques, which reduces the variance without increasing the bias. So what does that mean? Well, you can reduce the variance by saying, hey, I'm just going to do a regression line, but that may increase the bias. So what you want to do is, it's called regularization. In effect, reducing overfitting and regularization are almost synonymous. And I think the point here overall is simply, you do not want to overfit the data. The data must perform well on test scores with data it's never seen before. You want it to generalize well to new data by reducing overfitting or including regularization. We are going to code together, and overfitting is a topic that we will be looking at later and throughout this course. But first, let's have some fun.